Hello and welcome to MT3. We are now again going to look at some examples of solving partial differential equations using the method of separation of variables. Just to remind you, we are in Arfkin, Weber and Harris chapter 9 and Riley, Hobson and Benz chapter 21. Now there are good examples in both of these and I highly encourage you to read both of these in fact this is almost a requirement for the Arfkin. But I also would like you to read the Riley's chapter 21, where there are many more examples in these. So it's an excellent way of actually testing yourself. So how does this work? Now we've already seen an example of how this is done, this idea, in the last lecture. But let's go over this again. So we consider the wave equation in 1 plus 1 dimension. Now in the last lecture we used the method of characteristics to show that the solution psi, which is the function of x and t, will have some function f of x minus ct, that's a wave propagating along the positive x direction, plus some function g of x plus ct, which is a wave form propagating along the negative x direction. And let's see if we can recover the same using the method of separation of variables. So the ansatz is that our function psi, which describes the displacement at a point x at a time t, that's what it means. So just to remind you again, let's just draw an axis here. So if we have an x-axis, then what psi is, so you'll have some waveform, and psi is, so this is psi of x, this is x here, at some time t. So this is the displacement, okay? And now we got the ansatz is that psi is a function capital X of little x times capital T of little t. Now as before, what you need to do is find the equivalent of these differentials with respect to these two guys. So the second derivative of psi with respect to x is t times the second derivative of x with respect to little x. Now, important distinction here is that this is a partial differential on the left hand side, but but here it's a total differential, and it's a total differential because the function capital X is a function of little x only. There is no t dependence in there, and this is important because when we solve our differential equations, we want our constants will then be scalars, they won't be functions of t. And we can write this as capital T, the function capital T times x double prime. I find the prime notation to be quite useful when you're doing the separation of variables rather than using d by dx, that's quite cumbersome. In the same way, you have the second derivative of psi with respect to time, that can be written as capital X times t double prime. So our wave equation is then written as capital T times x double prime is equal to 1 over c squared capital X times t double prime. Now we divide by psi is equal to xt, and what that allows us to do is to write the left hand side as involving x only. Little x, this stuff on the left hand side is now a function of little x only. So it's capital X double prime divided by capital X. And on the right hand side we've got stuff which depends on little t only. So it's 1 over c squared times capital T double prime divided by capital T. So a function of little x only is equal to a function of little t only for all x and t, and the only way this can be true is it's equal to some constant, some scalar, which is independent of x and t. Now I've chosen the scalar to be k squared. You'll see why. It just makes our life easier. I have a question here before we move any further. We are dividing an equation by xt. Now what about the case when psi, meaning either x or t, is 0? Well, at those, as long as the zeros happen at isolated points, then at those points you cannot perform this division. So, but what we will hope is that there's some limit possible, so you can approach that point as close as possible and get a sensible value for these. This equation still is meaningful at the point in a certain sense. Yeah. As long as there are an isolated number of points, it shouldn't bother us. But if there are an infinite number of points, then we have to start to worry. So in this way, we can now write our partial differential equation as two different ordinary differential equations, two second order ordinary differential equations, one for x, so x double prime divided by capital X is equal to k squared, that's the first one, and the second one for t, 1 over c squared, t double prime divided by t is equal to k squared. Okay, so we can rewrite these as x double prime minus k squared x is 0, and t double prime minus c squared k squared t is 0. Both are second order ODEs with constant coefficients, so we can try the solution to find solutions of the form capital X, I should really make that capital X, is equal to e to the lambda small x, and capital T is e to the mu small t. This gives you a characteristic equation for lambda. So lambda is equal to plus or minus k, and this is why we use k squared. We didn't have to, but this is why we did. It avoids the square root appearing here. And then we have x as a function of little x is e to the plus and minus little k x. Okay. Now, I've made a comment here. There's nothing wrong with the solutions except that when we chose this scalar here to be positive k squared, we also implicitly kind of assumed, suggested at any rate that this is a positive constant, but there's no need for it to be a positive constant. In fact, it could be 0, it could be a negative constant, it could be a positive constant. We don't know what this thing is. It could even be complex. I don't know what it is a priori. So a priori, you've got to assume anything. Now, if you're after real solutions, then it's quite likely that this thing is a real number, but which sign does it have? We don't know. So we could have chosen minus k squared over here, in which case, instead of real exponentials, we would get complex exponentials. We could have chosen this to be 0, in which case x and t would not be exponentials of little x and little t. Instead, they would be linear functions of little x and little t. I ask you to show it for yourself. So there's much more there that's needed, and I've given you an example here. So if you choose k is equal to in, which effectively means we now have a negative constant, so these two parts, the x and the t part, are now equal to a negative constant, then we have solutions of the form e to the plus and minus in x, and t is e to the plus and minus I cn t. Now these are oscillatory solutions, which might be exactly what you're looking for if you're trying to solve a wave equation. And you might say, I'm not interested in solutions which are exponentially varying, because those don't look like wave solutions to me. So for physical solutions, which if you're looking for oscillatory physical solutions, then you might be after solutions like this one here. You might even be after solutions which are damped, in which case perhaps something else is needed. And all these possibilities exist here. They're all there, and it's just up to you to find out what they are. So if we take these oscillatory solutions as the ones we are after, then we can write down our general solution for x. I've indexed it now with little n, because we have a little n appearing here. So x of n, which is a function of x, is equal to some constant a n e to the I n x plus b n e to the minus I n x. Now I could just simply write this as a n e to the I n x. Why? Well, if I let n take 0 plus minus 1 plus minus 2, then you can see that if n can take positive and negative values, then these two could be regarded as just two instances of the same n. So n is equal to plus 1 would give you this one, n is equal to minus 1 would give you this one. So they are both encapsulated in here. In the same way, we could write the time solution, t of n, that's n and not r, is written as Cn times ICNT. Perhaps I should have called this Bn, but I didn't want to confuse it with this B here. So our general solutions then would be of the form psi n indexes the solutions, is equal to xn times tn, and we get this thing here where I've taken these two constants, little a n and little cn and call them capital AN. And I combined these two exponentials to give us the exponential of in times x plus ct. Now this is cool because earlier when we looked at the method of characteristics in the last lecture, we said that the solutions must be of the form some function of x plus ct. This is a traveling wave going to negative x, but we also said that there must be a solution of the form x minus ct. So where the heck is that gone? Well, the solution here is it's just lying hidden there. We kind of a bit sloppy. You see, when you combine the two functions x of n and t of n, we have a choice. So x of n could be e to the plus I nx, e to the minus I nx, and t of n could be e to the plus I nct, e to the minus I nct. Now you could either combine them plus with plus, minus with minus, which in fact gives you the solution above, or you could combine them crossways. And if you have e to the I nx combined with e to the minus I nct, you get the wave traveling to positive x. So we should have done the combination in a sensible way. We didn't, and that's why we got only 1. But the other solution is lying there, it's hidden in there. Now that's great because we found that the method of separation of variables does give us both kinds of solutions. Okay, a wave traveling along positive x, a wave traveling along negative x. Let's have a look at another equation. Wait, before we get there, I can't go any further without specifying boundary conditions, and we'll come to this topic soon. So for the time being, we have the general form of the solutions, that they must be like this, but I can't say anything more. What you can say, by the way, is that the full solution, and let's put this down here, the general solution, psi of x comma t, it will be some linear combination n goes from minus infinity to infinity of a n exponential of I n x plus ct plus bn, this is the waves traveling along the positive x direction, I n x minus ct. So this is the general solution. All right. Now what don't we know in the general solution? We don't know what an is, what bn is. C is part of our differential equation. It's a constant we know. And the sum goes over all n's. That's all I can say at this point. To find out more, we need the boundary conditions and we need the initial condition. Before we won't solve that equation here, let's go on to another kind of equation, the diffusion equation in 1 plus 1 dimension. In 1 plus 1 dimension, our diffusion equation is kappa times the second derivative of u with respect to x is equal to du by dt. So u describes, just to remind you, describes the concentration of something in a medium. Yeah, and this is the concentration with respect to time. So that's we're talking about the process where something diffuses from one point to another point in time. And kappa here is a physical constant that is greater than 0. It is our diffusion constant. So we are required to find the solution that tends to 0 as t tends to infinity. So now we are looking for a particular kind of solution, and let's see how this condition, which is a boundary condition, let's see how this condition simplifies our solution or causes us to choose one over the other. Okay, so we adopt the same strategy. U of x comma t is x times t, where x is a function of little x and t is a function of little t. Now I'm going to skip steps here because these are the same kinds of steps appearing again and again. You insert it into this partial differential equation, divide by xt, and what you should get is that x double prime divided by x is equal to 1 over kappa t prime divided by t. This on the left hand side is a function of little x only. This on the right hand side is a function of little t only. The only way they can be equal for all x and all t is that they are both equal to a scalar. I've called the scalar L. Okay, so let's now solve the equation. So let's solve the equation for x. So x double prime minus L times x is 0. T prime minus L kappa times t. Sorry, t prime is equal to L kappa times t. This can be solved easily to give you t is equal to e to the L kappa times t. Now, we have been asked to find solutions that tend to 0 as time goes to infinity, which means that L must be less than 0, because if L is greater than 0 or equal to 0, if L is equal to 0, we have t prime, we have time, the time part is a constant, it doesn't go to 0. If L is greater than 0, then this just exponentially increases. So we have to have L less than 0. So let us choose L to be minus lambda squared. Now I could have chosen it to be L is equal to minus lambda, but the lambda squared will help us soon. In fact, it's going to help us to solve this equation in a nice way. Okay, so we now substitute L is equal to minus lambda squared in these two equations, and that gives us x double prime plus lambda squared x is 0, and t prime is equal to minus lambda squared kappa t. Now this solution to the t equation is trivial. It's just the exponential of minus lambda squared kappa t. The solution to the x equation, this is an equation you have seen a million times now. It's e to the plus or minus I lambda x. Yeah, and this is why we chose this to be lambda squared, so that we don't have a square root in here. Now, if you're dealing with real problems, if you're dealing with a problem where diffusion is happening in real space, then keeping the complex exponentials is not a good idea. You might want to switch to the sines and cosines. This is up to you. I mean, both solutions are, of course, mathematically identical. So what we are going to do here then is to write our general solution. U of x comma t is a times sine lambda x plus b times cosine lambda x in brackets times this exponential in time e to the minus lambda squared kappa t, where lambda squared is greater than 0. And that's all we can say. This is a solution which decays to 0 as time goes to infinity, as long as lambda squared is greater than 0. What about a and b? I have no idea what they are. Yeah. We need boundary conditions. We need more conditions to find out what these things are. We don't have them yet. Now here's a question. Can lambda squared be 0? Now if lambda squared is 0, then x turns out to be, and I'd like you to check this, some constant a prime times x plus b prime. And t as a function of t will be some constant c. So is this allowed? I've already given you a hint earlier. Is this kind of a solution allowed? And the answer is no, but understand why it's not allowed. And once you've understood why, you will know why lambda squared has to be greater than 0, and we can't be greater than or equal to 0. Okay, now the next application is going to be the full solution, where we start to look at what are called superpositions of solutions, where we write our solution now as a linear combination of various parts. But that's going to be a long haul, so I'm going to save this, keep that for the next part of this this lecture. So we will end here on the separation of variables, coming back to the last example in the next part. Thanks for watching.